Have you ever wondered how a simple electronic circuit can create a perfect, clean signal, like a sine wave, just from a DC power source? It's a really cool engineering puzzle. Today, we're going to dive deep into one of the most classic solutions out there, the RC phase shift oscillator. And the best part? It's built from some of the simplest components you can find. Let's get into it.
So here's the challenge that engineers face all the time, especially when they're working with audio frequencies. How do you generate a nice, stable sine wave without using big, heavy, and kind of pricey inductors? The goal really is to be clever and use the cheap, tiny components we all have lying around, resistors and capacitors. This very practical problem is exactly why this circuit is so ingenious and important to understand.
All right, here's a quick look at our journey today. We'll start with the basic challenge of making something oscillate. Then, we'll cover the one unbreakable rule that governs all oscillators. After that, we'll tackle the main design puzzle, walk through the math that proves it all works, and finally, check out how it's built in the real world and what its pros and cons are.
So let's start at square one. What are we actually trying to do? We want to build an oscillator. You can think of it as a special kind of circuit that takes in a boring, steady DC voltage and magically turns it into a continuous, repeating AC signal. In our case, a perfect sine wave. It's like giving a circuit its own electronic heartbeat, one that it creates all on its own without any external signal telling it what to do.
Now, to make that heartbeat happen, any oscillator, I don't care if it's simple or super complex, has to play by a very specific set of rules. It's called the Barkhausen stability criterion. You can think of it as the two golden rules, the laws of physics for our circuit. If you don't follow them, it just won't work, period. And here are those two rules. They're actually pretty simple. First, the magnitude condition. All this says is that the signal, after going through one complete loop of the circuit, has to be at least as strong as when it started. If it gets weaker, the oscillation will just die out. Makes sense, right? Second, the phase condition. This one's about timing. The signal has to come back around to the start perfectly in sync, with a phase shift of exactly 360 degrees. That way, each new wave perfectly lines up and reinforces the one before it, creating a stable, continuous oscillation.
Okay, so how do we meet that 360-degree phase requirement? We use a clever divide-and-conquer strategy. We start with an amplifier that naturally inverts the signal. Well, an inversion is just a 180-degree phase shift, so boom, half our job is already done. That's the easy part. The real challenge, and the whole point of our design, is building a feedback network from just resistors and capacitors that can provide the other 180 degrees perfectly.
And that question brings us right to the heart of the RC phase shift oscillator's design. How in the world do we get a precise 180-degree shift using just an RC network? As you're about to see, just slapping one resistor and one capacitor together isn't going to cut it.
So let's ask the most obvious question first. Can we just use one simple RC circuit and call it a day? Is that enough to get us the 180 degrees we need? Well, the math gives us a very clear answer. Absolutely not. The phase shift of a single RC stage is governed by this arctangent function. And if you look at the graph, you'll see that as the frequency changes, the phase shift gets closer and closer to 90 degrees, but it never actually reaches it. It's a hard mathematical limit, so one stage is a definite no-go. Okay, so if one is out, what about two? I mean, if we could get 90 degrees from each, that adds up to 180, right? The problem is, to hit that theoretical 90-degree max, the math says our resistance R would have to be 0. And a 0-ohm resistor would just short our outputs straight to ground, giving us 0 volts out, a totally useless circuit. So the two-stage idea is another dead end.
And this leads us to the elegant solution. We cascade 3 RC stages together. The idea here is that each stage will contribute a portion of the required phase shift. Now, it's not as simple as each one giving us exactly 60 degrees, because each stage loads or affects the one before it. But here's the key takeaway. By using 3 stages, we can design a network that produces a perfect 180-degree phase shift at one and only one very specific frequency.
Okay, so we have our concept down. Now it's time to roll up our sleeves and prove it with some math. We're about to derive the exact formula for the frequency of oscillation and figure out just how much gain our amplifier needs to provide.
And don't worry, we won't get lost in the equations. Here's our game plan. We're going to use a technique called mesh analysis to write out the equations for our network. Then, we'll pop them into a matrix to keep things organized, solve for the circuit's transfer function, and then, this is the really cool part, we use a neat mathematical trick to find the exact frequency and gain our oscillator needs to work.
All right, let's kick off this derivation. Step 1 is to apply a classic circuit analysis tool called mesh analysis. We just define 3 little current loops, I1, I2, and I3, one for each of our RC sections. Then we use Kirchhoff's voltage law, which just says that the voltages in any closed loop have to add up to 0. This gives us 3 unique equations for our 3 unknown currents. Now that we have our 3 equations, the next step is to organize them neatly into a matrix. I know this can look a little intimidating, but it's really just a super clean way to write down a system of equations so we can solve it. And our whole goal here, the reason we're doing all this, is to find the value of that last current, I3. Why? Because I3 flowing through the final resistor is what gives us our output voltage, our feedback voltage, VF.
So after we solve that matrix, maybe using something like Kramer's rule, we get this really important expression. Now you might notice something a little funny here. This isn't the usual output over input transfer function. It's actually the inverse, input over output. We do it this way because it just makes the algebra a whole lot cleaner. But this one equation holds all the secrets we need about our feedback network's behavior.
And here it is, the climax of the whole derivation. To see how our circuit behaves at different frequencies, we replace the S variable with j omega. Now, think back. What do we need? A perfect 180-degree phase shift. In the world of complex numbers, a 180-degree shift is just a negative real number. There's no imaginary j part. So if we want to find the one single frequency that gives us our perfect shift, we have to find the value of omega that makes the entire imaginary part of this equation completely disappear. We literally force it to be 0. And look what happens when we do that. By setting that imaginary part to 0 and solving, this simple, elegant formula for the oscillation frequency just pops right out. This tells us the one and only frequency where our network provides the exact 180 degrees of phase shift we need, and it depends only on the values of R and C we choose. How cool is that? So we have our frequency. But what about the gain? Well, now that we've gotten rid of the imaginary part, we can go back and look at what's left of the real part of our equation. When we plug in our special value for frequency, the whole thing simplifies down to this. Vn over Vf equals negative 29. The negative sign confirms our 180-degree phase shift. And the 29? That tells us our feedback network actually shrinks the signal's amplitude by a factor of 29. Okay, so the math is done. We've proved that our network gives a 180-degree shift, but also weakens the signal by a factor of 29. So to satisfy Barkhausen's first rule, our amplifier has to make up for that loss. It needs an inverting gain of at least 29. Now, let's see how we actually build this thing. In the real world, you'll usually see this circuit built in one of 2 ways. On the left, we're using an op-amp. This is a really popular choice because it's super easy to set its gain precisely just by choosing 2 resistors. On the right, we're using a single BJT transistor in what's called a common emitter configuration. This can also get the job done, and it uses fewer parts. But no matter which one you choose, the job is exactly the same. Provide an inverting gain of 29 or more. All right, we've designed it, we've analyzed it, we've seen how to build it. Now it's time for the reality check. What are the actual pros and cons of using this oscillator? On the plus side, the advantages are pretty obvious. The design is simple, it's cheap, and because there are no inductors, it's really compact. This makes it a great choice for low-frequency stuff, like generating audio tones. But there are some big downsides. Its frequency isn't super stable. It can drift as things heat up or as components get old. It's also a pain to tune, because you'd have to change all 3 Rs or Cs at the same time. And finally, getting a stable gain of 29 out of an amplifier without adding distortion can be a bit of a challenge.
So, to wrap it all up in one neat package, the RC phase shift oscillator is all about teamwork. You have an inverting amplifier that gives you a 180-degree phase shift and a gain of at least 29. It works hand in hand with a 3-stage RC network that provides the other 180 degrees of phase shift and an attenuation of 29. Together, they perfectly satisfy Barkhausen's 2 conditions, creating a beautiful, stable sine wave at a frequency set only by R and C.
And there you have it, the RC phase shift oscillator, explained from the ground up. It's a really beautiful example of just how clever analog design can be. So I'll leave you with a final thought. In our modern world that's so full of complex digital stuff, where do you think a simple, elegant, and low-cost analog solution like this could still be the perfect tool for the job? Thanks for tuning in.